And if we can be wrong about something as basic and as fundamental as this, then in what other ways might we be mistaken?
Did either of you play cards?
I play a little poker.
You play poker?
No.
So you can shuffle cards, can you?
Oh, no.
No?
I let someone else
So
shuffle.
do you shuffle like this?
Yeah.
Yeah? That's called the overhand shuffle.
Okay.
Because if you don't shuffle cards that well, you can try this one. This one's pretty good. It makes a complete mess of the deck of cards. Some cards go back to face, and some of them are like back to back.
Our complete trust in temporal order is the reason why we delight in the obvious impossibility of magic tricks.
Go back to face and face to back. I said it makes a total mess. I'll just show you. Some of the cards, they're like face to back. Not very good for playing poker or blackjack. But if you press the button here, press the button, boom, snap your fingers, they all come out the right way, which is rather handy.
That's
pretty cool, isn't it?
Pretty good.
Wow. My job as a magician is to manipulate people's faith. Hi, how you doing? Let me stop you for a moment. People realise that things can't disappear and reappear. I'm going to run through the cards and you say stop wherever you like. If you do your job properly, you can make it look as though two things can be in the same place at the same time. And to that end, essentially, you can make it look as though you're manipulating space and time.
But believe it or not, this sort of behavior isn't always an illusion. Beneath the surface of our common sense world lies another world, where magical things really do happen, where the impossible can be made real, and where time can perform the most incredible tricks. That place is inside the atom. For years, scientists had assumed that in our universe there was nothing smaller than an atom. The very word atom, in fact, comes from the Greek word for indivisible. Then in 1897, an Englishman named J.J. Thomson made an astounding discovery that inside the atom there were even smaller particles called electrons. Thomson's discovery opened the door to the amazing world inside the atom, a world where everything, including time, behaves in a truly alien fashion. Physicist Ian Walmsley has been studying this microscopic world for almost 30 years.
When we get inside the atom to this world of subatomic particles, the ideas that we have about the way the world works completely have to change. We can't think in the same sorts of common sense terms that we think of in everyday experience.
In fact, this subatomic universe is so strange that time becomes chaotic. A startling discovery that emerged from the study of light. Light consists of individual particles called photons, known for their wave-like properties.
Waves have a very interesting sort of phenomenon. It's called interference. When two waves come together, they can add together and reinforce one another, or they can cancel one another out. And this interference is a ubiquitous property of all waves, not just water waves, but also light waves.
But in the early 1900s, scientists noticed something very odd about these light waves. Something that proves that time isn't always ordered. In this reworking of a classic experiment, once described as the most beautiful in physics, single photons, or particles of light, are fired down a darkened tube towards a camera, one at a time.
So we have here a very simple apparatus. It consists of a light bulb at this end and a camera at the other end that can register the light. And in between, the light encounters a pair of slits etched onto this piece of glass, through which the photons can pass on their way from the source to the camera.
The purpose of the experiment is to study the behavior of photons as they travel from one end of the tube to the other. To begin with, the individual photons are sent through just one of the slits.
Each of these dots arriving represents a single photon, so most of them are coming along this point. Some of them lie above or below that point, but the distribution is nice and smooth.
Now the second slit is opened up, and the experiment repeated. Each single photon must still pass through one of the two slits, so the results should still be the same. But what we actually find is this: an interference pattern, something that should be impossible.
What that implies is that the single photon is somehow going through both slits at the same time. It's not making a choice as to go through one or the other, but is going through both simultaneously.
In other words, each photon exists not just in two places, but also in two times.
So we have this very strange notion that this single photon can be in two different places at once. It could be delocalized. But we can think also of a single photon being in two different times. So both space and time have become delocalized and fragmented.
On the surface, we feel time is ordered, but that belies a different reality. We are totally unaware of the chaos and unpredictability that lies deep within the atom. Not surprisingly, our understanding of time comes from our everyday experience. And it's for this reason that we cling to yet another of our assumptions about time, that it never stands still. In fact, one thing that sets us apart as humans is the knowledge that time waits for no man. That time doesn't merely exist, but is constantly flowing. But one discovery proved that this isn't always the case. In 1971, astronomer Tom Bolton embarked on a project to observe a mysterious X-ray source called Cygnus X1, an object assumed to be a distant neutron star.
I started to look at Cygnus X1 because I thought it would be a good opportunity to determine the mass of a neutron star. And nobody had done that yet.
Cygnus X1, some 8,000 light years away, is one half of what's called a binary system.
The binary system is a pair of stars that are gravitationally bound to each other, just like the Earth is bound to the Sun, and they orbit about their mutual center of mass.
By measuring the speed and orbit of X1's binary partner, Tom was able to work out the mass of his neutron star. But the figure he arrived at was far, far bigger than the one he'd been expecting.
That turned out to be about 10 solar masses, with a significant error, but still way too big to be a neutron star. As far as I knew, the only object that would fit that description and produce X-rays was a black hole. So I said so.